Hi, hello everybody. I hope that all of you are doing well today. So today we will have a new session. And in this session, guys, we will talk about a new chapter. So if we go to the textbook, I will have the textbook here with me. So we'll start chapter 7. And as you can see here, guys, chapter 7 will be included in the final exam. So you are approximately done. And you did very nice work, guys, especially in the midterm exam. I really appreciate what you did. So in today's session, guys, we will talk about the previous lattices and how many type of previous lattices do we have. And also, guys, we will talk about how many crystal system do we have. So if we come, guys, to this side that you can see right here, so maybe I need to make this a little bit and move this a little bit to this side. So you can see here, guys, that we have 7 crystal systems and we have 14 Pravis lattices. What's the definition of the Pravis lattice? The Pravis lattice, guys, has one atom. So if you consider the unit cell from the Pravis lattice, so you should have one atom. You still remember, guys, how we did that for the simple cubic. So in the simple cubic, guys, of course, we have 8 atoms on those 8 corners, and each one of these atoms contribute with 1/4. So 1/4 with 1/8. So 1/8 times 8, so that will give you 1. So that's very nice, guys. And the simple cubic is considered as Pravis lattice. Why is that? Because it has one atom, and sometimes we call this kind of unit cell, we call it primitive cell. Okay, so if we come here and try to see how many crystal systems do we have, guys. So we'll see that we have 7 crystal systems. I will start right here with the cubic. It is a famous one, guys. You know that. And then I can move to the tetragonal. So tetragonal is another system. And we have here orthorhombic. So this is another system, guys. And also we have hexagonal. The hexagonal also is famous. We know that. We know what's the hexagonal unit cell. And then, guys, we go to the monoclinic and then come to triclinic and then end up with trigonal. So we can see that the trigonal right here can be considered as a branch from the hexagonal crystal system. So that's possible. But people classified the trigonal as a crystal system. So we need to respect that. So you can see in total that we have 7 crystal systems. And each one of these crystal systems, guys, is different than the other crystal systems. So for example, if I come to the cubic crystal system, so you can see that the height and the width and the length are equal. So A, B, C, the same dimensions. So you can see A is equal to B is equal to C. And you can see that we have a cube here. So the angles between those axes, so if we have, maybe I can use something here to show you that. So if we, for example, guys, try to draw that. So if this is z-axis and this is y-axis and this is x-axis, so x-axis and y-axis and z-axis. Okay, we know that there is an angle between z and x, and there is an angle between y and x, and also there is an angle between z and y. And if we are talking about the cubic crystal system, so what do we will have? We will have here alpha, and here we will have beta, and here we will have gamma. So alpha and beta and gamma, if we are talking about the cubic system, they are equal to 90 degrees. They are perpendicular to each other. And you can try to draw the cube here, as I did, guys, right here. So this is what do I mean by alpha and beta and gamma. So these angles, guys, between the axes are equal, and they are equal to 90 degrees. And that's very nice. But when we come to the tetragonal, so you can see that A and B are equal, but they are not equal to C. So C has different length, as you can see, but A and B are equal, as you can see. But we still have alpha, beta, gamma equal to 90 degrees, the angle between the axes, as I mentioned, guys. If we have Z and X and Y. If we come, guys, to orthorhombic, so you can see that A is not equal to B and is not equal to C. Different lengths, guys. So A and B and C are not equal. And you can see that alpha and beta and gamma still 90 degrees. So it's still 90 degrees, but A and B and C like have different lengths, guys. If we come to the hexagonal, so the hexagonal is famous, and I believe, guys, maybe I need to move this a little bit down, or I think I need to come here to prevent the light, okay? So you can see, guys, with the hexagonal, we have A and B, and A and B are down here. You still remember that, guys? So maybe we have this A and this B, for example, and this C. Alpha and gamma are equal to 90 degrees. So the angle between A and C is 90 degrees, and the angle between B and C is 90 degrees. But the angle between A and B is not 90 degrees, it's equal to 120 degrees. So this is the hexagonal, guys. And the hexagonal represents crystal system by itself. So that's very nice. And now we can move to the monoclinic. It's very nice to go, and very important at the same time, to go through them in order. If we come to the monoclinic, guys, you will see that A and B and C are not equal. Alpha and gamma are equal to 90 degrees, but beta is equal to 120 degrees. Kind of strange structure, and you can see that, guys, in the textbook. By the way, I can go to the textbook and show you that. Just to help you guys to see that. If we are talking, for example, I will have my glass here just to make sure that I can see what was written here. So we are talking about the monoclinic. So this is the monoclinic, guys. So this is the monoclinic. It should be this one right here. So this is the monoclinic, guys. You can see that A and B and C are not equal. Alpha is equal to gamma, and beta, alpha is equal to gamma is equal to 90 degrees, and alpha is equal to gamma is equal to 90 degrees, and beta is equal to 120 degrees. So that's very nice. I did my best here to have it drawn in a simple way, so you can see that. We can come now to the triclinic. What is the triclinic, guys? To define the triclinic, we need to know that A and B and C are not equal. They have different lengths. And at the same time, alpha and beta and gamma are not equal. So they are not equal to 90 degrees. They have different angles. And that can build the triclinic that you can see right here. Strange shape, guys. Yeah. It's still it's still, as you can see right here, but if you see this shape in reality, you will notice that alpha and beta and gamma are not 90 degrees, and A is not equal to B, is not equal to C, is not equal to A. Okay, if we go to trigonal, which is, as I mentioned, can be considered as type of hexagonal, or maybe like building block of the hexagonal structure, so that's possible. The only difference here, guys, you can see that in the hexagonal, A is equal to B, but it is not equal to C. But here we have A is equal to B is equal to C. Okay, so it looks like hexagonal building block, but the difference, guys, we don't have C anymore, but we have A is equal to B is equal to C. You still remember, guys, when we studied the hexagonal, we mentioned that A1 is equal to A2, but they are not equal to C. If we consider the trigonal, you will see that A1 is equal to A2 and it is equal to C. Okay, this is the difference, but we can consider the trigonal as a building block that can build the honeycomb or the hexagonal. Okay, and you can see that alpha and beta and gamma right here are not equal to 90 degrees. And also the angles, guys, look like different a little bit. So you can see here, guys, that alpha, if we're talking about the hexagonal, you can see that alpha and gamma are equal to 90 degrees and beta is equal to 120. But here, guys, we have alpha and beta and gamma are not equal to 90 degrees. So different than that structure, but it can help you to build that structure, guys, in different way. So, okay. So you can see, guys, that we have here 7 crystal systems, as I mentioned, and I described each one of these systems for you guys. And at the same time, we have 14 Bravais lattices. What do we mean here by 14 Bravais lattices? We will go through that one by one. So I will start with the cubic system, guys. If you still remember, guys, the cubic system, we still remember that we studied simple cubic, which I used here P to refer to the simple cubic. And also, guys, we talked about the body-centered cubic, and I used here I to refer to the body-centered cubic. And also we talked about the face-centered cubic, and here I used F. So with a cubic crystal structure or cubic system, we have simple cubic, body-centered cubic, and face-centered cubic. So we will have 3 Bravais lattices under the cubic crystal system. If we come to a trigonal, so with a trigonal, guys, we just have simple trigonal, and we have body-centered trigonal. Those are the only 2 crystal systems that we have for trigonal, guys, and that's why we have 2 here, 2 Bravais lattices. And if we come to the orthorhombic crystal system, you can see that we have simple orthorhombic, body-centered, face-centered, and side-centered. And what do I mean by side-centered, guys? So to simplify that for you, I think we had example talking about the side-centered. I believe, yeah, that was in one of my previous sessions. But I will have that drawn here for you guys. So if we have a simple cube, as you can see right here, we know that it is possible to have atoms on those 8 corners. So that's possible. If we have atoms on the corner, as you can see right here, so we call this kind of system simple cube, for example. And if A is equal to B, but it is not equal to C, as I can see right here with orthorhombic, also A is not equal to B and is not equal to C, as we can see with the orthorhombic, guys. So we need to have we need to have face-centered. And what do we mean by face-centered? That means the atoms can be located here at the faces, maybe one here, one here, one here, one in the back. So that's possible. Or maybe one here and one here, maybe one up and one down. So we have some of the faces without ions and the other faces with ions. So we call that face-centered. And if we try to define the face-centered in proper way, so we need just to have one atom here and one atom here. So that can be called face-centered. So one in this face and the other one in this face, or one of them in the back and the other one toward us right here. Okay, so this is face-centered. It can be one up and one down, one on the top surface and one on the down surface. And we know this kind of atoms will have 1/2 contribution, guys, to the unit cell. So this is what do we mean by face-centered. And that's why you can see that the orthorhombic has 4 Pravis lattices. And if we come, guys, to the hexagonal, so in the hexagonal, we just have one Pravis lattice, which is the hexagonal. So we don't have other Pravis lattices, which is the simple hexagonal. So the simple hexagonal is the only Pravis lattice here. Okay, and if we come to the monoclinic, guys, you can see that we have here, so I wrote that somewhere, it is right here. So we have 2 here, we have 2 Pravis lattices, we have simple monoclinic, and we have face-centered monoclinic. So we have 2 Pravis lattices here. And if we are talking about the triclinic, you will see that we have just one. So we have just one Pravis lattice from the triclinic, and it is simple triclinic. If I come, guys, to the last one, the last crystal system, which is a trigonal, you will see that we just have simple trigonal. So simple trigonal, which represents one Pravis lattice. So that's very nice. Now, guys, if you try to add all of these numbers together, so we have 3 from here, 2 from here, and 4 from here, and 1 from here, 2 from here, and 1 from here, and 1 from here. So you can see that the total actually is 14 Pravis lattices. And yeah, I believe this is how people pronounce Bravis, and I have heard like Bravis. So he is a French guy. So you can use Bravis or Bravis. So that's fine. But the most important thing, guys, that we need to know, we have 14 Bravis lattices and 7 crystal systems. These are the famous crystal systems, guys, that we know. What do we study, guys, in this semester? What did we study in this semester, guys? We studied the cubic system and the hexagonal system. This is what we studied here, but in general, we have 7 here, as you can see. And also, you still remember, guys, that we studied the simple cubic, body-centered cubic, and face-centered cubic. So we know how to do all of the calculations, like how R, the radius of the atom, is proportional to the lattice constant, what is the packing number, and all of that stuff. We did that with the cubic. And also, we did some of these calculations also for the hexagonal crystal system. But we didn't do for all of these, but it's a good idea to know that. And chapter 7, guys, will explain that to us in more details. Now, guys, we know how many crystal systems do we have. And also we know how many Pravis lattices do we have. Now, by knowing these Pravis lattices, guys, and these crystal systems, it is very important to introduce 2 important topics, guys, which are the point group and the space group. So what do we mean by point group and space group? And maybe next session, we will talk about this in more details. So if we are talking, guys, about the point group, which is right here, maybe I need to turn this a little bit to the right, to the left, I'm sorry, to the left, so you can see what do we have. So what do I mean by point group here? So what is that? This is new for us, and we don't know what's the point group is. Actually, the point group represents combination of symmetry elements. So there are symmetry elements, guys, associated with these crystal systems that you can see right here. And those elements, or the symmetry elements, are, guys, inversion, which has something, so inversion has something to do with the center of symmetry. So if we are talking about symmetry, there is a center of symmetry. So the inversion, guys, can happen about the center of symmetry. And there is another element called reflection, and reflection, guys, it is similar to what we have with the mirror. So if we have a mirror, for example, on this side, we have object here. So the reflection will give you object on the other side. This is what we can see using the mirror. And this is actually what will happen with this symmetry element, which is reflection. Okay. And the last one, guys, is rotation. So rotation is another symmetry element. And if I'm talking about rotation, so it's possible to rotate this. Maybe you can see that using this pen, but you can see that with the marker. So this can be considered as rotation. That's very nice. And also, this can be considered as a rotation, guys. Okay. So we have the rotational axis right here. So this is one option. And you can have the rotational axis, guys, right here along this marker. So we can have the marker rotating like this. So, okay. And I will explain to you guys what do we mean by symmetry under this operation, which is rotation. Rotation like this, or maybe rotation like this. Okay, so we'll explain that in more details. So this is what do we mean by rotation. But now, guys, if we try to look at to these elements, so we have inversion, reflection, and rotation. It is possible to have a combination between these symmetry elements. That's possible. You can have rotation reflection, that's possible, and maybe a reflection inversion, that's possible, or inversion rotation. So that's possible, guys. It's possible to have combination between these symmetry elements. And I know this topic's still complicated, guys, and mysterious, but I will try to explain that to you step by step, and we will come back here to this side. But for now, let's focus here. So the other thing that I would like you to know, guys, that the different combination, so the different combination of these symmetry elements give rise to different symmetry points. So that will give rise to different symmetry points. Let's go behind that and see what will happen. And here, guys, I'm talking about the crystal. So if we try to apply different combinations of these symmetry elements on the crystal, we will notice that we have different symmetry points. What do we mean by symmetry points here, guys? So what do we mean by symmetry points? So before we come to the symmetry points and try to talk about them, it is very important, guys, to talk about this kind of process, guys. So this kind of process, it must be noted that all the crystals don't possess all the symmetries. Okay, so they don't share the same symmetries, guys. We need to make sure that they don't share the same symmetries. okay? All the symmetries, for example. The different crystal system exhibit different different symmetries. And here, if I'm talking about the cubic crystal structure, for example, so the cubic crystal structure will have different symmetries than, for example, a tetragonal. So the tetragonal should have different symmetries than the cubic, and different than the orthorhombic or the monoclinic. Okay, so this is very important, guys, to know. And also, another very important thing before we come back and explain what is the symmetry points here, we need to talk here, guys, about how many combinations we can have under this number of crystal systems and this number of Bravais lattices. So how many combination of symmetry points do we have? Actually, guys, we have 32 combination of the mentioned point group. So we can call the symmetry points. So now we come to the symmetry points. We can call these points like symmetry points or point group. This is what do you mean by point group, guys. So we have 32 combination of the mentioned point group symmetry elements. Actually, we have 32, and this number right here is very, very important. And if we come, for example, to these systems, we will see that each one of these systems has different number of point groups. So let's see here. I believe you still see me, guys, correct? Oh, yeah, I think, yeah, the camera doesn't work, but I'm still recording the session. Yeah, I'm still recording the session using Zoom, so that's fine. So the camera is not working anymore, but you still see me through Zoom, and that's very important. Let's continue, guys. And now, if we come to the cubic system, so how many point groups do we have, guys? So you can see that we have 5 point groups, and I will talk about that in more details, guys, here. I will have the cubic system as an example, so you can see what I'm talking about. So we have 5 point groups. So the point groups for the cubic system is 5. The point group for tetragonal is 7. The point group for orthorhombic is 3. We have 3 point groups. And don't worry, we will talk about that. And for the hexagonal, we have 7 point groups. And for the monoclinic, we have 3 point groups. And for the triclinic, we have 2 point groups. And for the trigonal, we have 5 point groups. So that is very important. And if we try, guys, to have example from one of these crystal systems, and I prefer here to go with the cubic, it is the simplest example for us. And hopefully, guys, you are good with this side, because there is no way, I believe, yeah, maybe I can keep that, but the good idea, guys, to erase all of that and try to have the cubic as an example here, and try to explain to you why do we have 5 point groups here. So there is no way, so just I will erase this side. And I will come here and try to draw cubic. So this is a cubic structure. So we have something like this, or cubic unit cell. So you have something like this. So that's very nice. That looks good. I will try to finish the back side. of this cube. And maybe we add some atoms here. So we have everything drawn properly. So we have all of the atoms here, and this is very nice. Now, guys, how can we involve what we learned from here? So how can we involve the point groups to what we have right here, guys? Actually, guys, I will start with the first property, and the first property here would be reflection. And if we are talking about reflection, guys, it is very, very important to have the same structure. So we don't need to have like different structure. So if I come to this crystal, this unit cell, and let's assume that I have mirror right here, and I put the mirror exactly right here. So what I will see on the other side? Actually, I will see the same picture. There is no different. So the same image. There is no difference here. So what does that mean, guys? That means, so there is a symmetry under reflection. So that's very good, guys. If I have the mirror fixed right here, and then look at this mirror, you will see the same picture that we have right here. So there is a symmetry under reflection. So this is very nice. And now I'm going to look at this side and do the same thing. Oh, I forgot to add some atoms here. I'm sorry for that. So we should have some atoms here. And also, if I have the mirror fixed right here, so we'll have the same image in this side. So there is a symmetry, guys. And if I have the mirror also like this, so that will give me symmetry under reflection. So that's very nice. So one of these elements, which is reflection, it is included right here, which is very nice. Okay, so there is no big difference, guys. Now, let's talk about rotation and see what will happen, guys. Maybe it is a little bit complicated to talk about rotation, but I will do my best to show you that. So if we have rotation, or if we applied the rotation element, so what will happen? So that requires us to draw this simple cubic in very nice way. So we need to have this simple cubic drawn in very nice way. So we can have, okay, so I will do my best here to have it drawn perfectly. Maybe I need to have this a little bit higher. So we see that. And another one right here. So that's very nice. And then we need to close this side and then close this side and then close this side right here. So that's very nice. And then we need to make this a little bit shorter. And then draw another line right here. So that's perfect. And then I need to draw a line right here. And line right here. So now we have the cube, guys. And this is very nice. So let's try to apply the rotational, let's apply the rotation element. And I will try here to show you the back from the front. So this is the back. So the back with the dashed line and the front with the solid line. So hopefully that's clear, guys. So the back with the dashed line and the front with the solid line, as you can see. So now what I'm going to do, guys, I'm going to rotate this cube and see what will happen. I will rotate this cube like 90 degrees. I believe rotating this cube 90 degrees is enough. So, I mean, it is enough to go back to the same structure. So I will have here the rotational axis. So this is the rotational axis, guys. It is right here. So now you can see that when I rotate this cube 90 degrees, so I will have this point right here as a reference for you. So this is your reference, guys, okay? And I'm going to have a line between the center of the upper surface and go to this reference point. So now if I rotate the cube 90 degrees, this point will move here. It will be here at this point, and it will create here empty point, just to show you that, guys. So if I rotate this system 90 degrees, so this point will become here. Now, after this operation, so what will happen? Well, we'll see that we have the same structure. So there is no big difference. Actually, there is no difference at all. If I, for example, try to change the position of the rotational axis, maybe I can have the rotational axis to be right here, to be horizontal. So let's try to do that. So firstly, I rotated the system like this with 90 degrees angle, rotated that like this. Now I'm going to rotate the system around this rotational axis, and also by 90 degrees. So what will happen? If I do that by 90 degrees, guys, and also here we have 90 degrees. So if I rotate the cube 90 degrees, this point right here will appear right here. And after we do this rotation by 90 degrees and then look at to the cube, we will notice that we have the same structure. Actually, there is no difference at all again. Now I will change the rotational axis to be on the whiteboard like this, okay? So maybe it is hard to draw that. So now I need to rotate this cube. Maybe I can use the marker. Now I need to rotate the cube around this rotational axis, guys, by 90 degrees. So now what will happen? This point will become here. And when we look at to this structure, we will see that we have the same structure. There's no difference at all. So this is very nice. The symmetry is applied here under this rotation. Now we will do another thing, guys. So we did the rotation around these three axes. Now I will consider different axes here and see what will happen. Maybe the symmetry is not applied with the other axis. So let's make sure that the symmetry is applied. Otherwise, we are not going to consider the rotation as a point group. Okay, so I'm going to erase this rotational axis and also this rotational axis and also this rotational axis. Maybe we don't need this atom anymore, and also we don't need this atom anymore. Okay, so just do that. Perfect. So now we have this cube again. So now what I'm going to do, guys, I'm going to rotate the whole system from here. So I will try to have rotational axis go diagonally from here and go out from here. Look at, go through this point and go through the cube and then go out from this point and go out. So now we need to rotate this system and see what will happen. Actually here, guys, we need to rotate this system. We need to rotate the system here 180 degrees. This is what do we need to do, guys. So if we rotated the system 180 degrees, so imagine that you rotate the whole system 180 degrees. So what will happen? So I will consider 90 degrees first and see what will happen. Okay. If I consider it 90 degrees, so this point is here. So 90 degrees, it will be here. And okay. And the whole system that we have here will be on this side. Okay, let's consider 90 degrees. So by considering 90 degrees, guys, if we rotated the whole system 90 degrees, so we will see, guys, that the object will not have the same symmetry. So 90 degrees is considered strange because we need to have the same symmetry. We need to come back to the same position that you can see right here. So to come back to the same position, or if you look at to this cube, you'll notice that you have the rotational axis like this, and you have the cube like this. If you did rotation and achieved this position again, so that can be considered as symmetry under the rotation. So that means we need to rotate the whole system, guys, 180 degrees. Okay, so when we rotate the whole system 180 degrees, so this will go up and this will go down, and then rotate it again 180 degrees. So you can see that you return back to the same position. And that's why people call this kind of rotation like twofold rotation. You need to rotate the system once and then rotate it again, so you can come back to the same position. If I consider the other rotational axis to be maybe go from here and through here, so you will see the same result and you will have the same result. Maybe the rotational axis come and go through this point and come out from the other side and rotate the whole system once and do that again. So you will see, guys, that you will have the same position and the same shape, actually, with considering the rotational axis, of course, after you do twofold rotation. Okay, so this is when we consider this diagonal rotational axis. And it is possible, guys, to have another diagonal rotational axis. So the other diagonal rotational axis, guys, maybe comes from here. So I will do that. It comes from here, from this corner, the upper corner, and then go out from this corner right here. Okay, here, guys, if you rotate the system 180 degrees and then rotate it again 180 degrees, you will have the same position for this unit cell and also for the rotational axis. So you will see that symmetry can happen if we do twofold rotation for this cube. And now, guys, you can see that we have 3 operations under rotation, and we have 1 operation under reflection. I know that we did the reflection more than one time, but Actually, guys, we have the same thing, so there is no big difference. But when we did the rotation, guys, we noticed that we have three different rotational axes, and there is a difference between them because I need to rotate the object maybe twice to have the symmetry. Okay, so we have three from rotation element, and we have one from reflection, and also, guys, you will notice that we have one from inversion. And actually, guys, inversion can gather rotation and reflection together. So how is that? Let's explain that to you guys. So inversion, if we use the word as English word, you will see that inversion is something similar to reflection, but there is a big difference, guys. If we are talking about reflection here, we are talking about mirror reflection. But if we are talking about inversion, keep in mind, guys, that we are talking about this property. Okay, so I will assume, guys, that we have here. So let's assume that we have here rotational axis. So this is the rotational axis, and maybe here, maybe I have a line here, or maybe bond, and I have atom right here. So if I do guys rotation 180 degrees and then do reflection, so I will do rotation 180 degrees, so this atom will be here, and we know that. And after I do rotation 180 degrees around this rotational axis, what I will do reflection. So this atom will be here. So we'll have something like this. So we'll have the rotational axis like this, and then we will have the atom right here. Okay. So this is the original position, guys, for the atom. If we did rotation, the atom will move to this side. And when we do reflection, this atom will appear here. It will appear up. So that's why, guys, you can see that inversion has combination between rotation and reflection. It has combination between rotation and then reflection. Okay, so this is what we have, guys, for today, and hopefully it is clear. We will talk a little bit more. Actually, before I end the session, it's a good idea to show you how do we have 5 here. So we have 3 rotation, and we have 1 reflection, and we have 1 inversion. So okay, 3 rotation, 1 reflection, and 1 inversion. So that gives me 5 point groups. And we will talk about the symbols of these point groups, guys, next session. Okay, so we just started, and next time, guys, we will have example about the point groups symbols, and then we will talk about the space group. And I will show you the importance of this topic when we study solid state materials. Okay, so we are done for today. Thank you so much for attending the session, and see you next session, guys. Thank you.
Thanks. Bye.
Yep.